anyway. That much I got. So everybody can see the recording icon?
Yes.
Yes, ma'am.
Okay, great. So anything else, Tanya? I mean, just put it in the chat box because I'm not able to hear your audio. I'm so sorry. Okay, I'll just get to the iScribe anyway. Yeah. Okay, so hopefully everybody is able to see this. And if you remember last time, we actually tried to work out what is going to be X, all right? And here, what did we do? We essentially, now remember when you are working out these expectation values, I mean, remember you don't really have to worry about, whether you're using a sine or a cosine function, all right? You define your limits and the wave and the what do you call the particular uh, your wave function accordingly. Okay, so for instance, you can just decide that you are going to have the infinitely deep well from 0 to L or 0 to A. Okay, and then you can just work with the sine function. Okay, so there's no problem with that. If you do it from minus A to plus A, then of course you'll have to work with the cosine function for the ground state. Okay, for the higher state, I think it does alternate. If somehow my memory fails me, I think it should alternate, okay, between sine and cosine, right? So anyway, let me write it down now. So this, if you remember, we will take it from 0 to L, and then it was essentially root 2 by L. Sorry, I'm just, can I just cut this out and write it properly again? Okay, so this is 0 to L. You will have X, and then you will have essentially root 2 by L sine n pi x by L, okay, star, and then you have, of course, root 2 by L. I mean, this is a trivial step that I'm putting over here because all of you know that this is a real function, and thereby the conjugate will be exactly the same thing. So essentially, this is what we were supposed to work out, which all of you know will be 2 by L, 0 to L, x sine square n pi x by L dx. And I think I did make some goof up here last time about the integral, but actually I don't think it was a goof up. It was something I'd picked up from a standard integral. I'm a bit lazy when it comes to integration. Nitin suggested a good technique, the integration by parts according as per the Bernoulli formula. And I think, Nitin, if you could share it with everybody, if you haven't already, you shared it with me. Thank you so much. You can use that and run into integrations much faster. Okay, I mean, you can do your integrations much faster. But anyway, I told you this will essentially end up being L by 2. I think I was using A, wasn't I? Was I using A, guys?
Yeah, ma'am.
Okay, fine. So we will just put it as A, okay? I'll just put it as A everywhere. Sorry. Okay, better stick to the same notation. This 2 by A, and this is going to be A, and this is going to be A by 2. Okay, and I kind of, we had a discussion last time that essentially this is arising because of the symmetry above the middle of the well. All right. So here, of course, the middle of the well is A by 2. All right. But you could have it around, x is equal to 0 as well if the well extends equally on both sides. So whichever is the central point, that is going to be the expectation value. And as you can see, this is a constant, okay, for all eigenstates. Okay, so which means it does not matter what excited state the system is in, your expectation value of the position is always the middle of the well. Okay, kind of makes sense, all right, because it's bound. You see, it cannot go outside, it's always symmetric inside, all right, and thereby the expectation value of the position can be expected to be the middle of the well. All right, so now let us go ahead and try and do it for px. Okay, so how will you do it for px, please? Essentially, you will do it again 0 to A, and then you will put your root 2 by A sine n pi x by A star. And then instead of px, what are you going to put? Minus IH cross d by dx. Okay, so you can leave it, of course, as a total derivative because this is a one-dimensional affair. And then you have root 2 by a sine n pi x by a dx. Okay, so again, you will get your 2 by a outside and you will have essentially 0 to a. And then this, of course, will be a sine n pi x by a. And one could have also taken this minus IH cross outside. I didn't do it, but doesn't matter. You'll have a d by dx of sine of n pi x by a dx. Right? Yeah. So now what do we have? We have minus 2 IH cross by a. And then you will have over here 0 to a. You'll have a sine n pi x by a. And then sine, if I take a d by dx, I will get a cos, right? So I will get cos of n pi x by a. And then, of course, I'll have to divide it by, I'll have to multiply it by a n pi by a. Am I right, guys? Is this correct?
Yes, ma'am.
Okay, thank you. So now let's take it out. So we'll get minus 2 IH cross by a into n pi by a. And then you have a 0 to a. You have a sine n pi x by a. You have a cosine n pi x by a dx. Kindly do this integration. Tell me what you get. Please do it yourselves. You have it so
0,
far.
ma'am.
I mean, I know the answer, but I would like you guys to just do it for me and tell me.
0, ma'am.
0, ma'am.
Yeah. Perfect. Did everybody get 0?
Yes, ma'am.
Okay. So tell me, how did you get the 0? Did you actually do it using the integration or did you use some other technique?
Derivative of average value of x.
Okay. That's absolutely correct. Okay. So the point is you can do it like this, or you can use what is the better method, which is you can use your Ehrenfest theorem. Okay, and how does the Ehrenfest theorem work? Essentially, your P is going to be what? M d by dt of x. Now, what you could clearly see is that this guy here, okay, is time independent, right? Yeah, so it's time independent. Okay, and because it's time independent, of course, this is going to be over here equal to 0. All right. So again, momentum, okay, the fact that it is 0 also arises because of the symmetry of the wave function above the center of the well. Okay. So this is again something which is expected. Of course, now when we start doing x square and px square, it's not going to be that trivial, right? So here, please note again, this is independent of n. Okay, both of these are independent of n. So we have x, we have px. Now let's go on to x square. Okay, so what about x square? Again, all of you know this is going to be 0 to a x square, and then you'd have essentially sine square n pi x by a dx. Okay, so please go ahead, try and do this integration, all of you. I've done it in some painful method. Okay, so let me just try and do it myself also. So I essentially have done this into minus. Okay, so this is what I essentially did. So, okay, I think I missed out something over here. I missed out the 2 by 8. Sorry about that. Okay, so I will get essentially. Mhm. Do I get over here? I will get enough. Okay.
Ma'am, why don't you use the Bernoulli formula?
Ah, yeah. Not very used to it, Nitin. That's the only thing. Have you got the answer already, Nitin?
Ma'am, I did everything before the class, ma'am.
Oh, okay, fine. So, what's your answer? Tell me.
A square inside braces 1 by 3 minus 1 by 2 n square pi square.
Okay. So, just give few minutes to people. Let's see if they get this as well. Oops. Forgot to change the page. I'm very, very sorry. I'll just do this again. Okay. So, everybody good? Anybody else who has gotten this answer or something different?
I've got this, ma'am.
Okay, great, great, very nice. Anybody else? I shouldn't hassle people, I think. I would be one of those people who would be doing this integration till the end of the class. Okay, so just pay attention here. Let us just look, since we have both the expectation value of x as well as the expectation value of x square, one could then go ahead and calculate the uncertainty in x, right? Now, how does one do that? If you remember, it should be essentially this. Okay, so if you get x square, kindly go ahead and compute this as well. Okay, so this is how you will compute the uncertainty in the variable. Okay, so any variable, you basically take the expectation of, so as usually you would write it, it'd be essentially, okay, this is the standard way of writing it. Okay, so please try and compute that for me as well. So I'm just going to put up the value for sigma x here. Okay, so let's just put it's okay, it's power half. Okay, I think I'll write it down here again. Sorry, shouldn't try doing things so close to the edge of the. Okay, so kindly just ignore this. So progress, guys. Other people are getting this.
Correct, ma'am.
That's nice to have endorsement from one person at least. What about others? Okay. So did everybody get it? Put up your, put a thumbs up on your screen. Okay, Meda's got it. Good. Nitin has got it. All right, very good, Amreen. Very nice, Manikanta. Okay, wonderful, Shazia. I think, I should leave people alone. So let's just try and go ahead. And okay, good, Tanya, good. All right. So let's just try and go ahead and look at the next one, which is, of course, your px square, right? So px square, what will that be? So if you want to have px square, this, which we will also, of course, have to do again the same thing. And then you have root 2 by a sine n pi x by a, right? Okay, then you will have minus I h cross d by dx, sorry, minus I h cross d by dx. Then of course you will have your root 2 by a. Actually, there should be a star. Anyway, you all know now. Sine n pi x by a dx. Okay, so this is basically what it is. So you will get essentially, let's see now, what are the constants that we can take out. You will of course get plus I square, which will be a minus h cross square into 2 by a, correct? And then you have integral 0 to a you have a sine of n by x by a, and then you have d square by dx square of sine n by x by a. Okay, dx. Okay, so just try and go ahead and try and do this, please. I will put up the final answer. Just do this integration. I hope I've got the right thing. That's some easy stuff. Okay, so essentially give us a plus 2h cross squared by, I will say, a into n pi by a whole square integral 0 to a. Right? Okay, so the final answer that at least I got here is, yeah, I think it's, okay, this is what I got.
Correct, ma'am.
Yeah, good. At least it's matched with Nitin's. Everybody got this for px square? Okay, wonderful. What about the uncertainty in P? Great, great. You're calculating right now. Just do it. Go ahead. Okay, Zabiola has got it. Wonderful. Amreen too. Wonderful. So just now, yeah, try and multiply your sigma x into sigma p, okay? The product of the two uncertainties, and simplify that expression, okay? See what you get. I'll just go ahead and share my screen again. Oh, what happened? So is this okay? Have people got this as the product of the two uncertainties?
Yes, ma'am.
Good. Very good. Very good. Okay, Manikanta and Veda have also got it. Very good. Okay, Saviola. Right. Very nice. Okay, guys. So let's have a look at it. Yeah. So what you can see over here, please concentrate on this last expression, all of you. This is the product of the uncertainty between in X and in Px, right? And what you will realize is that there is now a dependence, which is of course has been there in both the Px square as well as X square. You also have a dependence over here on N. Okay. So obviously as N goes up, this will also go up. Correct? Yeah. So the uncertainty product is essentially going to increase as you go higher in the energy, right? The energy eigenstates, as the energy eigenvalue increases, so does the uncertainty. So of course, the uncertainty is going to be minimum when n is equal to v is n is going to be the smallest value. So if you put n is equal to 1, okay, you put n is equal to 1. So let me just put it. This is a trivial step. So nonetheless, you can calculate it and satisfy yourself, those who haven't done it already. You essentially, for n is equal to 1. So let me just, okay, I'll put it on the new page. Why do it here? Crowd it up and make it look worse. Okay, so for essentially n is equal to 1, okay, you will find that your sigma x, sigma px is essentially equal to, my calculation gave me about 0.568 h cross, okay, which is of course greater than or equal to h cross by 2. H cross by 2 of course is 0.5 into h cross. So it is greater. So it definitely satisfies the uncertainty limit. Even in the minimum uncertainty position, which is for n is equal to 1, your sigma x into sigma px is greater than h cross by 2. Okay. And for, as I told you earlier, the ground state, okay, n is equal to 1 is closest to the uncertainty limit. And this you can take as a given, okay? Please take this as a given, all right? You may be asked this questions for other states, but remember the ground state is usually the minimum uncertainty state, okay? So any comments about this? If this is done, then we shall close this problem. Any comments, please? Any doubts, anything that you felt that wasn't correct, or you have an alternate way of doing any part of it? So the two key things that we learned over here, okay, one of course is that we calculated a whole bunch of expectation values, right? So we did it for the position, we did it for momentum, position square, momentum square. We learned to calculate the uncertainties. Very important is the use of the Ehrenfest theorem wherever necessary. Okay, if you have to calculate your what do you call it, expectation value of the momentum, you already have the expectation value of the position, kindly just use Ehrenfest theorem. Okay, it will just save you bunches of time. No point in doing all the integration. Here I just did the integration so that you know that it works. All right. So the point is, because otherwise you just do a d by dt and you say, hey, anyway, it doesn't have an dependence on time, it's a stationary state, so what the heck. So I wanted you to do it the other way also, to convince yourself that yes, it works. All right. Yeah. So otherwise, sometimes what happens, we think that these are all in very exotic situations we use this, we don't use it in this commonplace affair. You do. Okay. Yeah. So use Ehrenfest theorem whenever you can. All right. And the next thing is that the ground states, okay, are usually the ones which are closest to the uncertainty limit, and you can calculate the uncertainty. And we have just done the whole explanation, whole detailed working of how. All right. So any doubts, please, so far? Otherwise, we will move on to the next problem. Any doubts? Okay. So let's move on to the next problem. Ah, sorry, I didn't mean to share this. Okay, I'm not even sharing, I'm doing some nonsense. Yeah. So let's have a look at here, this particular file. Right. So have a look at the last problem, please. All right. So here we have an infinitely deep square well, and it has its initial wave function is an even mixture. What do I mean by an even mixture? The weight factors for both the states is the same. Okay. So it is an even mixture of the first two stationary states, which means the ground state and the first excited state. Okay. So your psi x0 is nothing but a psi 1 x plus, it's actually chi1 x plus chi2 x. Okay, where chi1 and chi2 are essentially the ground and the first excited state. Yeah. What are we supposed to do now? We are supposed to normalize x0. We then are supposed to find what is the time dependent form, right? This is at time t is equal to 0. We have to find the time dependent form and find, of course, the probability distribution at a particular time. And then for that, we calculate what is the expectation value of x, what is the expectation value of p. Yeah. And then ask the question, what would be the energy of this value of this particle if one measured the energy, and how does it compare to E1 and E2. Okay, so this is basically what it is. Now let us just look at the uh, you know part D. I think all of you now you are completely sure how you're going to do it. How are you going to do it, please? Part D, anybody just volunteer and tell me how you'll do it. What happened? Am I audible? Suddenly I get doubts. If you've already calculated part C, all right, how would you go ahead and do part D, please? There is some problem.
Ehrenfest theorem.
Yeah, absolutely. Just do Ehrenfest theorem, okay? Don't need to do anything else. Now, the last part, okay, what you saw. Okay, just 1 second. Yeah, the last one which you saw, all right, which is essentially you have been asked, if you measure the energy of this particle, what will you get? Okay, so can anybody volunteer this answer? What will you get? What will you get if you measure the energy of this particle? Any ideas? Okay, so let me just take you back to formalism. All right. In formalism, what did it we kind of said certain things, all right, that when you make a measurement, all right, what will you measure? You will actually measure an eigenvalue of that particular operator, all right. So here you're trying to measure the energy. So the measurement will always yield an eigenvalue of the energy operator, which is nothing but your Hamiltonian. Okay. So if the ground state energy is E1 and the excited state energy is E2, what will you measure? You will always be measuring. Remember, the system is sitting in a mixture of E1 and of the ground state and the first excited state. Correct? So you will either measure E1 or you will measure E2. Is this clear to everybody? You will only measure an eigenvalue, but you will measure it with a certain probability. Okay. So as I said again, when you have a system which is in an admixture of eigenstates, okay, so here it is in an admixture of the eigenstates of the Hamiltonian, correct? It is in the energy eigenstates. I am trying to measure the energy. I will only be able to measure an eigenvalue. All right. So here, since it's in the mixture of the ground state and the first excited state, every time I measure, I will either measure ground state energy or I will measure first excited state energy. Now the question is, with what probability? Can somebody tell me what is likely to be the probability?
0.5.
Yes, absolutely. Half the time I will measure E1, the other half of the time I'm going to measure E2. Okay, so let me just get back there again. And why do you say that? Because look at the weight factor here. Okay, the A is the same for the excited state as well as the for the ground state as well as the excited. The weight factor is identical. So thereby, half the time I'm going to measure E1, half the time I'm going to measure E2. So in some sense, without even doing all, the complicated calculations or whatever, the expectation value of the Hamiltonian is going to be what? If half the time I'm measuring E1, half the time I'm going to measure E2, I'm going to get the average of E1 and E2 as my expectation value of the Hamiltonian. Okay. That is what I'm going to get. And so you know this answer already. Find the expectation value of the Hamiltonian. How does it compare to E1 and E2? I think you know the answer already. Okay. Yeah. Without having to figure out what is A. All right. As long as you know the infinitely deep well, you know the ground state energy, you know the first excited state energy, you already know this answer. Okay. Given, if you find out the expectation value of X using Ehrenfest theorem, you already know part D. So now what our job is essentially to do the first three parts. Okay. That's about it. Is this clear? Yeah. Any doubts, please, in what I explained about this problem? We just broke it down into various pieces and had a look at it. Okay. So everybody's clear about the final part, how to go about it? Any doubts, please? Yes, no, very good. I'm fast asleep, ma'am. Okay, good. Anybody else, please? Okay, good. I'm happy that people have understood. Thank you. Thank you. Okay, fine. So now let us go ahead and try and solve. First of all, let's try and get the normalization, correct? Yeah. And then we will try and get the time dependent wave function. Okay, I think poor Sahana was somehow she lost connectivity with us. Sahana, are you there with us? Okay, I don't know whether she can hear me or there is some audio disturbance again. Fine. So let's go on, guys. Let's try and solve this particular problem. So what do we have over here? As I said, so let me just draw a line after this thing. Okay, so our problem essentially has given us a wave function x0, which is sitting something like this, right? Okay, so this is your chi1 x, plus chi2x. Correct? And the first job, of course, is to normalize and this, of course, I think everybody knows how to do it. So just let's go ahead and do it, please. Okay, your psi of, so go ahead. You don't have to really look at my solution. Okay, I forgot the A. Okay, trivial steps nonetheless. Important thing to realize is that this guy here and this guy here, what will happen to them, please? I'm not sure I have a class at all. Any suggestions? What is going to happen to those two integrals, please? Okay. What do we know about these eigenstates, please? What are they? Any suggestions? See, the eigenstates of the infinitely deep well, they are eigenstates of the Hamiltonian, right? We all know the Hamiltonian is Hermitian. So please take this as a fact for all Hermitian operators. What is going to happen to their eigenstates of a Hermitian operator? They are orthogonal, aren't they? Yeah. What do you mean by orthogonal? That their inner product is going to be 0, correct? Yeah. Is there anybody there? Are you people listening? Yes?
Yes,
Zero
ma'am.
is the
Okay.
difference, ma'am.
So now the point is that if they are orthogonal, all right, okay, this term here and this term here, they are nothing but the inner product, right? Of here chi1 with chi2 and here chi2 with chi1, right? Yeah. So these are nothing but essentially, if I want to write it in, it's chi1, chi2. inner product. This is nothing but chi2, chi1 inner product. Correct? And since these are orthogonal, they are going to be both 0. Okay, so what are you going to be left with then? Implies you will have mod a square. You'll have just a 0 to a. What are these on the other hand? We have already normalized, right? These functions. So this is going to be 1. This is also going to be 1. So what will you get for your a, please? Okay. Is this good? I mean, look, you can do it. You know, this particular case, I think it was a bit trivial. But if you see an even admixture of two, just 1 second. Okay, maybe somebody dropped something else. All right. So the point is, if you have an even admixture of two functions which have already been normalized, you know that the normalization constant for that will be 1 by root 2. Okay, this is a given. But this technique, I just wanted you to see it because just in case you had over here a C1 and a C2, okay, instead of a, then you may have to work it out a little more carefully. All right. Yeah. So that is the only reason why I kind of showed you this. All right. And I hope everybody is convinced that this A is going to be 1 by root 2. All right. Yeah. Again, you can do a lot of these things just by examination. Okay. So this could have been done by examination. The reason, again, as I said, I'm doing the working out is so that if it is non-trivial, you can still do it. Okay. Using the same technique. Is this clear? Everybody good? Are you guys there? Yeah. All right. Fine. Yeah. Fine. Let's go on to the next bit of it. What's the time right now? Okay. Oh, fine. So it looks like I'm already out of my time. All right. So now let us just write down your psi xt. I will just write it down. Okay. And then we will just stop it over there. Okay, so your psi of xt is going to be what? It is essentially going to be nothing but summation over n is equal to 1 to, sorry, I don't know why I'm writing this. It doesn't matter really. Over here, what will it be? Yeah, there's no need to write the summation at all. So we can write it as 1 by, okay, I made a mistake, haven't I? Your integration should have been, nobody, I think everybody has fallen asleep or something. I did a mistake, right? It should not be 1. It is 1 indeed, but then it goes from 0 to a, right? Correct, guys? Hello? I don't know. Maybe it's 1 by root 2. I'm getting completely confused now. Okay, so let's just go here. So we have what? 1 by root 2, 2 by a, sine of, so n will be first for this, right? Pi x by a. Okay, and then you have e to the power of minus I by h cross, and then you have the ground state energy.
New page.
Oh yeah, sorry. Very sorry. I'm making mistakes all the time. All right, so let's just give me 2 minutes. I'll wrap up, okay? So your psi of xt will be essentially nothing but 1 by root 2. Now you will put in the first thing, which is sine pi x by a. And here you will have e to the power of minus I by h cross. And we will put in the first ground state energy, which is going to be h cross square pi square by 2 ma square into t plus again 1 by root 2, again root 2 by a, and then you'll have sine of 2 pi x by a e to the power of minus I by h cross, and then you'll have essentially 4 times this, right? So 4 h cross square pi square by 2 ma square. So this is your xt. So please note that the time dependence, okay, all right, for each of these states is determined by the energy at that particular state. Okay, so it is not going to be as non-trivial as you would have thought earlier. Okay, so there is different time dependencies associated with different parts of it. Okay, so what we will do is that we will take up this problem, okay, in the next class. All right, and then hopefully we'll be able to wrap up at least infinitely deep well in the class itself and move on to simple harmonic oscillator. What I'm going to do is that today I'm going to also send you a whole bunch of numericals. Okay, yeah, so I mean, not just numericals, they're going to be simpler problems, a whole bunch of infinitely deep well problems, but simpler problems. And those you don't need to send it back to me as an assignment. Okay, once you all tell me that you have solved all of them, I will send you the answers. Okay, just the answers I will send you. You can compare, and if there is any discrepancy we can discuss those in class. Is that okay? Is everybody okay with that?
Yes, ma'am.
Okay, so I will send you those numericals either today or tomorrow. Okay, I will just put it up on the drive. All right, and you guys can just do it. And once all of you tell me that yes, you have solved them, I will put up the solutions for that. Solutions in the sense, not the worked out solutions, just the answers. Okay, fine. Okay then, so I think we will stop today's class. I was hoping to have solved this the second problem totally. It somehow didn't happen. Doesn't matter. And as I said, we are going slow right now so that we can pick up pace later. All right. So this one, I just want to do it slowly and thoroughly. Okay then. So we will stop.